Welcome to The Explainer. Today, we're going to break down one of the most elegant, truly beautiful concepts in all of physics, electromagnetic waves, and we're doing it specifically for your NEET prep. We're going to build this whole thing up step by step, starting from a tiny little inconsistency and ending with this grand, unified picture of the universe.
Okay, let's just dive right in. Think about it. A radio signal, the light from a bulb, an X-ray, on the surface, they seem to have absolutely nothing in common, right? But believe it or not, they're all part of the same big family. And the story of how we figured that out? Well, it all starts with a brilliant puzzle that had 19th century physicists scratching their heads. And the solution? Well, it changed everything.
So our story begins with a law you probably know pretty well, Ampere's circular law. It's a cornerstone of electromagnetism. But the genius James Clerk Maxwell noticed something weird. A little inconsistency that just didn't sit right with him. Something he couldn't ignore. All right, so the basic idea of Ampere's law is simple, right? An electric current, that's just charges flowing, creates a magnetic field that circles around it. And for a simple current-carrying wire, this works perfectly. It's clean, it's reliable. But Maxwell found a very specific situation where this simple law just seemed to break down completely. Okay, check this out. Picture a wire that's charging up a capacitor. Now, if we imagine a simple, flat, circular surface that the wire punches right through, Ampere's law works like a charm. The current I goes through, and we can calculate the magnetic field, B. No problem. But here's where Maxwell's genius really kicks in. He asks a simple question. What if we choose a different surface? And this is the heart of the whole problem. Look at this weird pot-shaped surface. It has the exact same circular rim as the flat one. So the magnetic field along that rim has to be the same. But here's the catch. No actual charge, no current, passes through the bottom of this pot in the gap between the capacitor plates. So according to the old law, the current is zero, which means the magnetic field should be zero. How can it be both something and nothing at the same time? This was a massive paradox. The law was broken. So to fix this paradox, Maxwell came up with a really radical idea. He imagined a whole new kind of current, one that didn't involve any moving charges at all. He called it the displacement current. So you really got to get this distinction. Conduction current, which we can call IC, that's the one we're used to. Electrons physically moving down a wire. But displacement current, ID, is a whole different beast. As that capacitor charges up, the electric field in the gap between the plates is changing. It's getting stronger and stronger. Maxwell's big idea was that this changing electric field in that empty space acts just like a real current. And here it is, the one simple term that fixed everything. The displacement current, ID, equals epsilon naught times the rate of change of the electric flux. That's d phi E over dt. Now, don't let the term scare you. Just think of electric flux as the amount of electric field passing through a surface. So a rapidly changing electric field means a big displacement current. A constant electric field, no displacement current at all. This was the key. With this new piece, Maxwell fixed the law. He just added his new term right into Ampere's law. So now the magnetic field is created by the sum of both the regular conduction current and the displacement current. So in the wire outside the capacitor, you've just got IC. But in the gap between the plates, you've just got ID. And the beautiful part is, the law now gives the exact same correct answer for the magnetic field, no matter which surface you pick. Paradox solved. So with this one, simple fix. Maxwell's 4 big equations of electromagnetism were finally complete. And when he put them all together, they predicted something absolutely incredible. Waves of electric and magnetic fields that could just sustain themselves and travel right through the vacuum of empty space. Think about this for a second. We already knew from Faraday's law that a changing magnetic field makes an electric field, and now Maxwell's new law showed the reverse. A changing electric field makes a magnetic field. Do you see the beautiful symmetry there? One creates the other, which in turn creates the first one, and on and on and on. They basically leapfrog through space, regenerating each other as they go, with no need for any air or water or anything to travel through. Okay, this next part is what's truly mind-blowing. Maxwell took the fundamental constants from his equations, mu naught from magnetism and epsilon naught from electricity, and he used them to calculate the speed of these theoretical waves he just predicted. And the number he got was about 3 × 10⁸ meters per second. That was the exact experimentally measured speed of light. It couldn't be a coincidence. Light itself is an electromagnetic wave. All right, so that's the theory. And it's amazing. But for your NEET exam, you've got to know the nitty-gritty, the specific properties, the formulas that describe these waves. So let's break down the practical details that you're actually going to be tested on. So the most important thing to remember is their geometry. EM waves are transverse. All that means is that the vibrations are perpendicular to the direction the wave is moving. And to be really specific, the electric field vector E, the magnetic field vector B, and the direction the wave is going are all mutually perpendicular. Just picture a 3D coordinate system with one on the x-axis, one on the y-axis, and the wave zipping along the z-axis. Okay, this one is a must-know formula for NEET, for sure. The peak strength of the electric field, we'll call it E0, divided by the peak strength of the magnetic field, B0, is always equal to the speed of light c. They're locked into this constant ratio. It's a super useful relationship for solving problems. And never forget, this value, c, is one of the most fundamental constants in the entire universe. In a vacuum, every single electromagnetic wave, from a lazy radio wave to a high-energy gamma ray, they all travel at this exact same speed. And of course, the classic wave equation totally applies here. The speed of the wave, c, is just its frequency, nu, multiplied by its wavelength, lambda. It's that simple. If you know one of them, you can always figure out the other, because their product always has to equal that constant, the speed of light. So let's see how this one single idea, electromagnetic waves, explains this huge range of stuff we see all around us, all organized just by their wavelength or frequency. And here's the whole family, all laid out in a row. You've got radio waves with wavelengths bigger than you are, microwaves, the infrared heat you can feel, then that tiny, tiny slice of visible light that our eyes can actually detect, then UV, X-rays, and finally the super high-energy gamma rays. They are all the exact same thing, oscillating electric and magnetic fields zipping along at speed c. The only difference between a radio wave and an X-ray is its wavelength. That's it. Okay, let's pull back and put this all together. To make sure this really sticks in your head for revision, we're going to create a clear, logical map of this whole chapter. This is it, the entire story in 6 simple steps. You start with a problem. Ampere's law was broken. Then you remember Maxwell's brilliant solution, the displacement current. That led to the complete symmetrical equations, which in turn predicted EM waves. Then you just have to know their basic properties. And finally, you understand how they all fit together into the whole EM spectrum. Use this flow, and you'll have this chapter locked down. And let's just end on this thought. Maxwell's discovery didn't just unify some equations. It totally changed how we think about a vacuum. It's not just empty. It's this dynamic stage where fields can dance and ripple and carry energy across the entire cosmos. That's how powerful this idea is. Keep asking those big questions, and good luck with your preparation.